Hello again. Here's lecture 301 on chemical equilibrium. And it's very important to note that engineers must be concerned with the yields that chemical reactions have. Companies that employ you want to know how they can maximize profits by increasing the production of products from chemical reactions. Now, unfortunately, not all chemical reactions go to completion. Some chemical reactions actually reach states of equilibrium, where the products recombine to produce the reactants, and reactants and products are being produced at the same time. When the rates at which they're being produced equal, we say the system is in equilibrium, and delta G is equal to 0 at that point. So it has to be known how to manipulate chemical equilibria so you can maximize the yield in a chemical reaction. So we're going to learn all about chemical equilibria. So in a chemical equilibria, typically systems are closed. Nothing is entering or leaving. It's in an enclosed space. And when a system is in equilibrium, there's no evidence of any macroscopic changes. And the equilibrium is reached through a spontaneous process. There's no energy that needs to be inputted. Just arrives at it once it starts. A dynamic balance between the forward and reverse reactions is established. The temperature is constant, which means it's isothermic, and it can happen from either direction. So to give you an example of an equilibrium that demonstrates there's something dynamic happening, if you take a saturated copper iodide solution and place radioactive iodine in the system, with non-radioactive silver iodide sitting in the bottom of that solution, what happens over time is the iodide ion, which is radioactive and can be traced, will actually be found in the silver iodide sitting at the bottom of the solution. Now, what I want to illustrate with a piece of software that comes from the University of Colorado, it's PHET is the name of the website. There's a link below here. And I'm going to show you how to get to the web page. Once you get to the web page, basically what you want to do is select salts and solubility and download it to your computer. Since it doesn't play off the internet, it has to be downloaded. You need JavaScript on your computer, which most computers have. If you don't have JavaScript, you'd be well advised to install it. And what I want you to do is go to slightly soluble salts and select copper 1 iodide. And then you're going to grab that molecular dispenser and shake it. So I'm going to show you what that looks like. So here it is. So I shake it. This is copper 1 iodide. And you'll see some of it is dissolved, but some of it is not dissolved because this isn't a very soluble substance. And if I add more, you can see that the amount of dissolved copper and the amount of dissolved iodide are equal and they're not changing anymore. But more important, you'll notice of the dynamic nature of what is happening here. The reaction doesn't go to completion. The copper and the iodide, the copper are the green and the iodide ions are in red. What happens is when they collide with the surface at times, if they're going slow enough at the right angle, they actually will form part of this precipitate at the bottom of the solution. And at the same time, for every iodide ion, red ion that joins the fray, a new iodide ion is liberated on average. Same thing happens with the copper 1 ions, the green ions. So if you watch it carefully, you can see again there is an equilibrium that's established. The macroscopic properties that you're observing are not changing. The amount of solid in the container is not going to change. The quantity of dissolved copper ion and iodide ion in the solution are not changing. It's in a state of dynamic equilibrium. So that's a good example of it. So to get back here, so now in any reaction, change in concentration of reactant and product molecules can represent an example like this. Here we have two reactants, A and B, and they're in equilibrium with product C. Now that's from the perspective of left to right. If you're looking at right to left, of course, 3C is the reactant and A and B are the product. What's noteworthy is when this system is in equilibrium, what it means is the rate at which A and B are converted into C is the same as the rate at which C is converted into A and B. So if we add A and B to start this equilibrium in equal quantities, we can study over time the changes in quantities of A and B. And this is where the stoichiometry of the reaction now tells us what kind of changes we're going to see to A and B and C over time. So as you can see from the graph, A and B will not change by the same amounts. Because 2 moles of A are consumed for every mole, 2 moles of B, sorry, are consumed for every mole of A, the quantity of B will go down twice as much as the quantity of A. And the quantity of C will go up 3 times as much as the quantities of A goes down. Now, I can show you from the graph here, again, shows you the how the stoichiometry affects this equilibrium. When equilibrium is established, the quantities of C, A, and B are no longer changing. We've reached a dynamic equilibrium. Does that mean it's come to a halt? Absolutely not. Just like that dynamic equilibrium we looked at, the copper iodide, there's still reactants forming products and products forming reactants, but the rates at which that is happening are equal. So again, you can see the amount of C has changed by 3 times as much as the quantity of A that has decreased. So again, that comes from those coefficients in the balanced equation. And basically now, if for each mole of B consumed, you're going to consume 1.5 moles of C. You're going to produce 1.5 moles of C. Now, is there a limiting reagent? No, nothing ran out. It's because it's a dynamic equilibrium, reactants forming products, products forming reactants at the same rate when equilibrium is reached. So, like I said, there's a continuous exchange of particles. When equilibrium is reached, that's not going to change. So to someone observing the system, no change in the macroscopic properties are happening since the quantities of C, A, and B at equilibrium are not changing. So a system sometimes is not at equilibrium because the reaction may be so slow that the change is simply not observable. That's another situation that can unfold. So reactions take on many different appearances. Some chemical reactions appear to go to completion. For instance, the example we've cited before is an acid-base. We have a strong acid and strong base, and they combine to make salt and water. And the quantity of products is much greater than the quantity of reactants. So the K value will be very, very large. This is an acid-base neutralization, as I've said. We have the strong acid and the strong base. So in solution, HCl particles and NaOH particles do not exist. They only exist as ions, as does the sodium chloride exists as ions. There's no molecules of sodium chloride in this mixture. So remember, acids are noteworthy for their itchy burning sensation if you get them on your skin. Bases feel slippery like soap. A lot of soaps are made out of bases, but they balance the pH of it to eliminate the burning sensation. Of course, nobody would buy soap if it burned you. So when you get an acid or base on your skin, remember, never use an acid to neutralize a base or base to neutralize an acid when it's on your skin. You simply wash it off with water. And that's because the neutralization reaction is exothermic and it makes the situation worse by burning you. So now some reactions don't seem to go at all. For instance, I have ethane and water to make ethanol and hydrogen. The K of that particular reaction is pretty small. So the concentration of reactants is much greater than the concentration of products. That reaction is not very spontaneous. Still other reactions seem to go partially. where we can have nitrogen gas and hydrogen gas combining to make ammonia. There's an equilibrium there. This particular equilibrium is one of the most economically exploited equilibria in the world. It's the Haber process, developed by Fritz Haber, maker of poison gas for the Nazis. And that particular equilibrium mastery created what is called the Green Revolution. We could then take nitrogen out of the air, combine it with hydrogen from fracked natural gas, or from natural gas that's been separated, the hydrogen from it, and we could make ammonia, and we could replace the nitrogen in our soil that is used by protein generating plants very quickly, artificially. And that led to increases in yields for many, many products. So types of equilibrium systems we can talk about are homogeneous gas phase systems. A homogeneous system is one where everything in the equilibrium is in the same phase. They're all gases here, two NO2s making N2O4. We can have heterogeneous equilibria where we have different states of matter. We can have calcium carbonate solid can be in equilibrium with calcium oxide and carbon dioxide. Notice there's solids and there's gases. That's why we call it a heterogeneous equilibria. We have silver chloride in an equilibria with its two ions. And again, notice on the right there are aqueous particles, meaning they're dissolved ions, and we have solids. So it's heterogeneous because of the different states. We also can have equilibria involving acids. In this case, acetic acid in equilibria with hydrogen ions and acetate ions. Another name for acetic acid, of course, is ethanoic acid because it's got two carbons, prefix being F. It's an organic acid. Organic acids always end in OIC, so ethanoic acid. The systematic name, acetic acid, common name, an even more common name for the solution is vinegar, 5% acetic acid. So it's an excellent preservative. It was discovered years ago, so we can grow vegetables in northern climates and preserve them for the long winter ahead. Pickles are one of my favorite, I have to admit, because it inhibits bacterial growth. The food will stay fresh for quite a long period of time. Now, we're going to talk about how we can discover the value of equilibrium constants. If we have a typical equilibria involving two reactants A and B, producing products C and D, with stoichiometric quantities of little a, little b, little c, little d involved in this equilibria. It doesn't matter what quantities of A, B, and C, D are initially placed in the container, or whether you just start with A or B or start with C or D. The end result, the equilibrium constant, will always be the same at the same temperature. This is known as the law of mass action. So we can establish that an equilibrium constant K is really the reverse reaction over the forward reaction. So recall your equations from reaction kinetics. So in this case, equilibrium constant K is the concentration C to the power C times the concentration D to the power D divided by the concentration of A to the power of A times the concentration of B to the power of B. So this numerical expression, again, the equilibrium constant. So for a homogeneous system, we are going to include all the participants because they're all in the same phase. So now we can say, if we use concentrations, we can use the subscript C to denote the equilibrium constant using concentrations. So the concentration of N2O4 in moles per liter divided by the concentration of NO2 squared, which would be moles per liter squared, is going to equal Kc. Or we could use another value for an equilibrium constant, which is going to give us a different number. We could use Kp, where Kp is derived from using the partial pressure of the gases in the equilibrium mixture. Partial pressure of N2O4 in the mixture divided by the partial pressure of NO2 squared in the mixture. So now recall, Vp equals nRT. It's equation you're well versed in. So now if I'm going to rearrange the equation in terms of the pressure of NO2, I end up with number of moles of NO2 divided by volume. Well, isn't that what we call concentration? So now we can see the concentration of NO2 in that equation. So the pressure of NO2 is really the concentration of NO2 in moles per liter times RT. We're going to use that equation later on. So for heterogeneous systems, notice now with different states present, solids and gases, the equilibrium expression, in this case Kc, would be the concentration of CO2 gas only. The concentrations of solids don't change in this equilibrium. They remain the same throughout, so it's not included in the equilibrium calculation. Okay. So Kp for the solid would be the partial pressure of CO2 gas. In this case, because they're solids again, they're constants, they're not used in the equilibrium Kp expression. So another example, silver chloride solid in equilibrium with its two liberated ions in aqueous solution. Silver chloride is not very soluble. In fact, it precipitates quite easily. If you take a soluble solution, let's say of silver nitrate and combine it with sodium chloride, you're going to get a precipitated silver chloride, and it will form an equilibrium between its two ions, silver ion and chloride ion. And we can come up with an equilibrium constant. In this case, we call it a solubility product constant. Because there's a solid on the left-hand side, it is a constant. It doesn't change. So the equilibrium constant Ksp is only equal to the concentration of silver times the concentration of chloride ion. Now, in the event it was something like, let's say it was a 2+ ion here, then it would be, the ratio would be 2 to 1, and there would be a square term in the Ksp formula. So now for an acid-base system, again, we can come up with an equilibria. And we call the equilibria, in this case, will be the concentration of hydronium ion times the concentration of acetate ion divided by the concentration of acetic acid, HC2O3. We leave out water again because it's a constant that doesn't change. And we can come up with an equilibrium constant K, use subscript A to indicate it's the equilibrium constant for an acid. Now we can do the same thing for a base. And a base, we simply call the equilibrium constant a Kb for weak bases, and we'll look at those later. Now, the significance of the size of the equilibrium constant K. The size of K tells us a great deal about the ratio between the quantity of products and the materials on the right versus the materials on the left, which we traditionally call reactants. If K is very large, it means it's product favored. It means there's way more products at equilibrium than reactants. If K is small, the reverse situation happens. There is mainly reactants, the material on the left, as opposed to the products. And if the K value is near 1, the concentrations of reactants and products are near each other, close to each other. So calculating K for a homogeneous gaseous system. So we can, again, we're going to use the equilibrium equation, A and B in equilibrium with C and D. So, sorry, I forgot to put 2 arrows there. So just think that there's an arrow here and an arrow there. So if the reaction involves solutions where concentrations are given, K can be evaluated by direct measurements of the concentrations of all participants in this equilibrium. And we know from previous example that Kc is equal to the quantity of C to the power C multiplied by D to the power of D, divided by the concentration of A to the power of A times the concentration of B to the power of B. So if the reaction contains gaseous species, K can be evaluated using the partial pressures of each gas, in which case we're going to use P here instead of C. Okay. So Now, Kp would equal this equation. Again, we're putting C, partial pressure C times raised to the power C times partial pressure D to the power D divided by partial pressure of A to the power of A times partial pressure B to the power of B. Okay, so now I just want to change my pen here. Whoops, sorry. Okay, so now in equation 1, we can, for the homogeneous system here, again, we have the same equilibrium, A and B in equilibrium with C and D. It's possible to obtain both Kc and Kp values. Kc rarely equals Kp. So again, remember PV equals nRT. P is equal to N divided by V. When we rearrange this equation, divide both sides by V. In which case we can say the pressure of A is equal to the concentration of A, which is the same as number of moles divided by volume, moles per liter, times RT. Therefore, Kp, again, we can use the equilibrium expression and get an equilibrium mathematical relationship. So we can also replace the pressure for C as the concentration of C times RT to the power C, concentration of D to the power times RT to the power D. Similarly, for A and for B, we can mathematically do the same thing. So we end up with expression of concentration C to the power C times concentration D to the power D divided by the concentration of A to the power of A, concentration of B to the power of B times RT. And we're going to look at the difference between, we're going to add C and D up and then subtract A and B, because C and D are in the numerator and A and B are in the denominator. When they're exponents, we subtract the exponent from the denominator from the exponent in the numerator. So we end up with an expression, we know this, where we use concentrations. It's called the Kc, equilibrium constant derived from the concentrations. So we're going to replace this part of the equation with Kc, and we still have RT. And again, we're going to look at the change in the number of moles in the reaction. How does the quantity of C and D compare to the quantity of A and B? So in essence, we're going to take the mole of gaseous products and subtract the mole of gaseous reactants to figure out what delta N is. Now let's look at this example using, again, the Haber process, producing ammonia from nitrogen and hydrogen at 472 degrees Celsius. The equilibrium concentrations are given for hydrogen, for nitrogen, and for ammonia. And we want to find the equilibrium constant Kc for this reaction using concentrations. So we know the concentration is going to be the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. So when we plug our numbers in, we end up mathematically with 0.105 moles or molarity to the power of 2 minus 4, because 3 and 1 add up to 4 here. 2 minus 4 is minus 2. So the unit for Kc is molarity to the minus 2. Again, molarity is moles per liter. So it's moles per liter to the minus 2. So if I wanted to write it, I could write it as moles per liter to the power minus 2, or I could flip-flop and it goes liters squared per mole squared. Different ways of expressing the same quantity. Now, at a different temperature, 500 degrees Celsius, let's find Kp. If we're given these quantities for pressures of nitrogen, hydrogen, and ammonia. So now we can use our equilibrium expression. Here, we say the quantity of ammonia squared, again, the partial pressure of the quantity of ammonia squared, divided by the partial pressure of nitrogen, divided by the partial pressure of hydrogen cubed. So we take the values given to us for ammonia, we square it, take the value given for nitrogen, and take the value given for hydrogen. And mathematically, when we work it out, again, look at the units. It's atmospheres to the power of 4 on the bottom, atmospheres to the power of 2 on top. Sorry, forgot to put atmosphere right here. And we end up with 1.45 times 10 to the 5 atmospheres to the minus 2. Now, would Kp equal Kc times RT to the power of change in N? Because N changed here. We had 4 moles and 2 moles, so it changed by 2. Well, the answer is no. They would not be equal because the temperature has changed. Since the temperatures are different, Kp and Kc would not equal one another. That is only good when the temperature stays the same. Now I'm going to look at a second example of an equilibrium. Hydrogen and iodine in equilibrium with hydrogen iodide. Noteworthy to note, there's 2 moles of hydrogen iodide for each mole of hydrogen and iodide. And we're given the initial quantities of iodine and of hydrogen. They're placed in the container. The system is not at equilibrium at that point, but equilibrium does get established, and the quantity of iodine has been found to drop to 1.065 times 10 to the minus 3. So we want to calculate all the equilibrium concentrations. So what we're going to do is set up a table which we call an ICE table. I stands for initial, C stands for change, E stands for at equilibrium. So what was given to us? Well, we know the concentration of iodine at equilibrium and the concentration of hydrogen at equilibrium. And we are also told the quantity of iodine that was present at equilibrium. So we're going to put that down here. Well, we can now figure out how much the iodine changed. The iodine quantity went down because when there's only hydrogen and iodine in the container, the only thing that can happen is it reacts to produce hydrogen iodide. And also note that you're going to make twice as much hydrogen iodide as the quantity of iodine that was consumed and the quantity of hydrogen that was consumed. Now, if iodine went down by 0.935 times 10 to the minus 3 moles per liter, then hydrogen had to go down by the same amount because it's a 1-to-1 reaction. But hydrogen iodide had to go up by twice as much because the ratio is given by the stoichiometry of this equilibrium expression. So we know, again, it's going to go up by twice as much. So at equilibrium now, we can figure out the amount of hydrogen iodide that must have been present, even though we're only given the amount of iodine. And we also know how much hydrogen had to be present. So we are now ready to calculate, because they're in moles per liter, we're going to calculate the Kc for concentration. So we know it's going to be equal to the hydrogen iodide quantity squared, concentration, divided by the concentration of iodine, divided by the concentration of hydrogen. And most common mistake students forget is the 2 here, they forget to square the hydrogen iodide. So again, we're going to take that quantity at equilibrium and square it, and we're going to divide it by the quantity of hydrogen multiplied by the quantity of iodine. Now in this case, molarity squared divided by molarity, this is going to be unitless in this case because there's 2 moles of product, 2 moles of reactant, they cancel out. So when we do the mathematics, we get a value of 50.5 as our Kc. Now let's look at a third example. This is an equilibrium involving sulfur dioxide and oxygen in equilibrium with sulfur trioxide. And what we're given is the amount of SO2 gas had a pressure of 1 atmosphere. We mix it with oxygen gas at a pressure of 0.5 atmospheres. At a temperature of 1100 K, we put it in a sealed container. Now at equilibrium, the pressure of the system was found to be, the total pressure was found to be 1.35 atmospheres. So a little bit more of a challenge here. So let's calculate the partial pressure of each gas at equilibrium. Also calculate the equilibrium constant Kp, because we're using pressures of gases, it's called a Kp. So now there's our equilibrium. We make an ICE table. we're going to input the data that was given in the question. So we were told the original amounts in atmospheres of SO2, NO2, and we were also told the total pressure. Now, since sulfur dioxide and oxygen were added to the container, this system has to shift to the right before equilibrium can be established. So we're going to use up these two substances at the ratio of 2 to 1, and we're going to make SO3. Again, the amount of SO3 produced is going to equal the amount of SO2 consumed. It's going to be twice as much as the amount of O2 that was consumed. All we're given is the total pressure of the system, which is the pressure of all three gases. So again, we're going to have to make some assumptions here. So we know that SO2, in order to reach equilibrium, has to go down by 2x. The amount of oxygen has to go down as well, because again, the system goes left to right to establish equilibrium. We know that SO3 is going to go up by 2x. So now we can establish, if we started at 1 atmosphere pressure and it goes down by minus 2x, we know at equilibrium it will be 1 minus 2x. And oxygen, 0.5 minus x, and SO3 is 2x. Well, is there any way we can find out what x is? Well, of course. We're told the total pressure is 1.35 atmospheres. So we know that the total pressure is equal to the sums of the pressures of each of the gases. And we know the pressures of the gases in terms of x. So we know the total pressure, 1.35 atmospheres, must be equal to the pressure of SO2, which is 1 minus 2x, added to the pressure of oxygen, which is 0.5 minus x, added to the pressure of SO3, which is 2x. So when we group our x terms together, minus 2x and x, add up to 0, we're going to be left with minus x on the right. And when we group 1 and plus 0.5, we're going to have 1.5 atmospheres minus x on the right, 1.35 atmospheres total. So now we're going to simply add x to both sides and subtract 1.35 atmospheres from both sides and end up with x equals 0.5 atmospheres. Now, we're not done yet. That simply tells us what x is. We were asked to calculate the quantities of each of the gases. So we now know the quantity of SO2 will be 1 minus 2x. Well, if x is 0.15, 2 times 0.15 is 0.3, 1 take away 0.3 is 0.7. We know the quantity of O2 in atmospheres will be 0.5 minus 1.15, which is 0.35 atmospheres. And the pressure of SO3 will be 2 times x, which is 0.30 atmospheres. Now that we've established how much of each of the gases is present in equilibrium, we can calculate Kp. So Kp will be the pressure of SO3 squared divided by the pressure of O2 divided by the pressure of SO2 squared. So mathematically, you can show it with that expression. We can substitute our numbers in and perform the math. 0.3 squared divided by 0.35 divided by 0.70 squared is 0.525 atmospheres, which is Kp, equilibrium constant using pressures. Now recall the mathematical expression again. The relationship between Kp and Kc is given by that expression. So we can rearrange the equation to find Kc now. Kc simply equals Kp divided by RT to the power of change in N. Is there a change in N? There certainly is. We started with 3. We ended up with 2 moles in this equilibria. It's always products take away reactants. So 2 take away 3 is minus 1. Delta N is minus 1. And so if we take 0.525 and divide it by 0.08206 times 1100 K, take all that to the power minus 1, then we end up at 47.4 liters per mole, the value of Kc. Again, I'm showing it's a decrease in the moles of gases right here, which I've already talked about. So suggested homework to read and to do some examples out of the textbook and problems from the book. Of course, the answers to these problems are in your answer book. So I hope you enjoyed the lesson. Signing out.